In this video, we'll discuss some practical non-Bayesian ways for obtaining uncertainty estimates in deep learning, which often actually still define the state of the art. Let's dive right in. Alternative treatments of uncertainty in neural networks. A very popular approach for obtaining uncertainty estimates in deep learning is via ensembling. This works as follows. First, you construct an ensemble of M neural networks on your training data, and I'll talk more about the various different approaches for constructing such an ensemble on the next slides. Then, for each test data point, you simply predict with each of these M networks, and you get this prediction f sub I for the ith network, and then you combine the outputs, these predictions f sub I, of these M networks in order to obtain probabilistic predictions. So for the case of classification, the individual networks actually already output probabilistic softmax outputs. So there the f sub I is probabilistic already. And we simply average these probabilistic predictions of the individual networks in order to get an overall predictive distribution of our ensemble. For the case of regression, there the networks typically only output point predictions, f sub I, and there we compute the empirical mean and the empirical variance of these individual predictions. Basically, if all of your M networks actually predict the same value, then you're relatively certain. And if they predict very different values, then you're uncertain. So this is a very natural way of quantifying our uncertainty via the ensemble. There are different ways in which you can actually construct these ensembles. One that is very popular is MC dropout, and we've seen that before, of course. So you use dropout as usual in training, and in the end, in order to make predictions, you sample M dropout masks, and those define M networks that you can then use in your ensemble, just like we saw on the previous slide. Previously, when we talked about MC dropout, we only said you would average these predictions in order to get a regularization effect, but you can also take into account that these different dropout masks give you different networks, and you can quantify the uncertainty by looking at the empirical variance. A key reason why MC dropout is very popular is that there is literally no overhead at training time. You use exactly the same training procedure you use for standard neural network training with dropout. So the training phase doesn't actually change at all. And then you could even take a network that you trained half a year ago, as long as you still have the possibility to sample dropout mass and predict with each of them, then you don't even need to redo the training at all. But you can just directly get uncertainty estimates by sampling different dropout mass and predicting with the resulting networks. Of course, while you don't have an overhead at training time, you do have an overhead at test time still, because you need to make M predictions. But this is going to be the case for any ensemble method that is based on M networks that we'll look at. So MC dropout was the first approach for getting an ensemble of M neural networks. And the second one is, well, Markov chain Monte Carlo. We already saw in the video on MCMC that we actually get this chain of our weight vectors, and from that chain we take M of these weight vectors spaced in regular intervals, and those then define M ensemble members that we use in order to get a Monte Carlo approximation of the mean, but we can also use these in order to get an uncertainty estimate. The third approach for constructing ensembles that we're going to discuss is exceedingly simple. You just use different random seeds and fit M different networks based on a different initialization with a different random seed and SGD. And this results in M different networks because a different initialization typically yields a different network, because when you start in different regions of the space, SGD runs to a different local optimum. I would really like to highlight that this approach is surprisingly effective. even in 2019, this was still shown empirically to yield state-of-the-art performance. And you can apply this really easily for any network that you can fit, as long as you have the time to fit M models. And in contrast to something like MCMC, this works all the time, and the networks you get are less correlated than the ones you would get in MC dropout. The fourth approach to get an ensemble of M networks is to run SGD with restarts, short SGDR, and we've seen that approach before. And as we've seen, SGDR cools down the learning rate with a schedule like this, and then heats it up again, cools it down, and heats it up, and cools it down, and heats it up, and so on. And then we can actually just use these intermediate convergence points where we have cooled down the learning rate. We take the weights of the neural network, save them away, and then actually through that get our ensemble members. And of course, this doesn't have any overhead in terms of runtime because this is just a single optimization run. The alternative would be to have a slow annealing over this entire period. And that would only result in one network that actually had this learning rate cooled down, and so one network that had converged. While in SGDR, you're getting these M different networks, in this case here for free. Of course, then at test time, you still have the M-fold overhead, just like in MC dropout, and you need to save these M networks. So out of these four approaches, currently the best performing one in practice actually tends to be this deep ensemble approach of doing M refits with different initializations, but it can also be combined with SGDR to basically do several different refits, and in each of the refits, you actually use SGDR in order to get more than one network out of a single refit. So you reduce the time for training. You can also create ensembles of neural networks by exploiting that different hyperparameter settings lead to different networks. And the resulting hyper deep ensembles approach has recently been shown to actually yield new state-of-the-art performance and to also outperform the previous deep ensembles. And this is very nice because you can directly reuse the hyperparameter evaluations that you have done with a hyperparameter optimization for your neural networks. So you get the individual networks that result from the different hyperparameter evaluations and just save them. And then in the end, you can combine this in an ensemble. And this has been done for quite a while before. But only recently it has been shown that this is actually really effective for deep learning. A similar and concurrent approach to create ensembles that actually comes out of my group is to exploit that different architectures yield quite different predictions. So we are assembling different architectures, not hyperparameter settings as up there. So recall that in the video on Bayesian reasoning, we said that being Bayesian is about taking into account all sources of uncertainty. And while all of the approaches that we've talked about so far actually fix the neural architecture, in practice, there's not only the parameter uncertainty we need to worry about, but there's also architecture uncertainty. And different architectures often yield very different predictions, so networks with different architectures tend to be quite uncorrelated, and that's great for ensembles. And indeed, you can extend neural architecture search to an approach we call neural ensemble search, in which we find not only one good architecture, but a set of architectures that can be combined into a strong ensemble. And this approach has recently led to new state-of-the-art results outperforming deep ensembles of the best single architecture and also these hyper deep ensembles up here. Okay, so after we've seen how we can get empirical uncertainty estimates via ensembles, let's now focus on another approach, how we can get predictive uncertainty estimates for regression tasks via parametric output distributions. So we can actually train a network to directly output the parameters W of a parametric model. And the parametric model is going to be from probability of the output y given the inputs x and the parameters of this parametric model. And the most common form for this parametric model is going to be a Gaussian, where the weights w actually parameterize the mean and the standard deviation. So you would then have a neural network with two outputs in the end, one for the mean and one for the variance. However, for robustness, you wouldn't actually task the network to output the mean and the variance directly, but you would rather actually have the network output the mean and the log of the variance. Why is that? Well, the variance has to be positive, and if the network actually was to output a negative variance, well, that would mathematically not be okay. So rather, you now have two outputs of the network, mu and the logarithm of the variance, and then you can simply take e to the power of the second output here in order to get the variance for your Gaussian. The way we train our network to output this parametric model is simply by maximizing the log likelihood of the data under that predictive parametric model. And we can do this, as usual, by maximizing the log likelihood with respect to our network weights, theta. So when we output a Gaussian distribution, you just compute the log likelihood of the data under that predictive Gaussian. So each of these log likelihoods would then be the log likelihood of a particular Gaussian, namely the output under the predicted weights for this particular input x sub I with these network parameters. And to make predictions for a new point, you then just compute the outputs of the neural network for that data point as an input by a simple forward prop, and then you interpret the outputs w as the parameters of your predictive distribution. For example, in our case of a Gaussian, this predictive distribution is a Gaussian with a mean and a variance that are the outputs of the neural network with these network parameters and for this input here. Okay, so we discussed ensembles on the one hand, and we discussed these predictive uncertainty estimates on the other hand. And these two ideas can actually also be combined. In this case, each network I in our ensemble with weights theta sub I predicts a probability distribution, not a point estimate anymore, but rather it has this predictive uncertainty estimate. And it's going to have a mean that is different for each of the ensemble members and a variance that is different for each of the ensemble members. And we can then combine the predictions of each of these ensemble members. And since each of these ensemble members now already predict a parametric distribution, we can combine these in a mixture distribution. So intuitively, in this mixture distribution, we want to combine the uncertainty of each of our individual networks. And if the individual networks disagree in terms of their mean, then we also want to increase our uncertainty correspondingly. And we can do that by using the so-called law of total variance to compute this mean here and this variance of the mixture distribution. And this variance actually computes the disagreements between the means, just like in the standard deviation. But then it also adds the individual variances of each of the networks. And in this way, you get an uncertainty estimate that takes into account that each of your networks is uncertain and that there's also disagreement between your individual networks. We actually use this combination of ensembling and predictive uncertainty estimates for a particular application that we did in a collaboration between my lab and Thomas Brox's computer vision group here in Freiburg. The problem we tackled there was optical flow, which is a particular type of dense regression task in computer vision. And for this, we used a network architecture developed in the computer vision group called FlowNet. The standard FlowNet here does not have any uncertainty prediction. Then in ensembles, we actually have M of these FlowNets, and each of them has a single output. Then in the predictive uncertainty case, we have a single FlowNet, but it has two outputs, namely the mean and the variance. And then in the combination, we have M of these FlowNets, each of them having a mean and a variance prediction. One additional approach that we also had in that paper was to actually do all of that in a single network. So there we had one FlowNet that would actually produce M different hypotheses, and each of these hypotheses would have a predictive mean and a predictive variance. And then we would have a network following that, here called the merge net, that would merge these M hypotheses into a single hypothesis with a mean and a variance. And this is particularly interesting for this dense regression task here, because in that case, actually depending on where you are in the image, which pixel you're currently predicting for, you can actually learn to trust different networks in your ensemble more than others. And in this case here, we can do all of that in a single network using end-to-end learning, so doing forward props and backward props through this. And this actually worked very nicely. So as desired, we would get large uncertainty estimates in the regions where the FlowNet actually makes some errors. Well, here's an example of that. Here's an image of the Kitty dataset, and really there's two successive images like this in the data. So there are only a few things moving in this image, particularly this car and this pedestrian here. And notice that here there's also this error being made where the shadow of the car is being predicted as moving. And while shadows are very hard to predict, and it's quite common that optical flow predictions make some mistakes there, as we see here, this is actually also the region where our predictive uncertainty is high, whereas the predictive uncertainty is much lower in these areas where we're actually right. So while we can't actually easily get rid of these errors, we can, in this case here, quantify our uncertainty about the different predictions, and we at least don't have these predictions where we're really certain about a prediction, but it's wrong. And in the slides, there's also this video here that you can click and see additional examples of this and additional details. So for now, let me conclude this video and also actually the whole lecture on uncertainty by saying that well, no network is perfect, but especially in safety critical applications, it really helps to know when we don't know. So we might make mistakes sometimes, but the goal is that in those cases, we're at least also saying that we're uncertain. I think this is a very important topic, and it's also a very active research topic in the community. And in this week's lecture, I hope that you've gotten a good overview of the types of approaches that are out there for solving this problem. All right, that brings us to the end of this video. And as always, I'd like to leave you with some questions. I encourage you to pause the video here and think about them to activate the material. And this is also the last video of this week. So I'll see you next week. Thank you.